So this is 2019 FRQ number 3. You have a projectile launcher, a sphere, and so a student hypothesizes that the spring constant of the spring inside the launcher has the same K value for different compression distances. So the student plans to test the hypothesis by launching the sphere using the launcher. So for part A1, state a basic physics principle or law the student could use in designing an experiment to test the hypothesis. Since friction is not mentioned, we can assume that friction is negligible and therefore energy is conserved. So, conservation of energy, or this equation, energy initial equals energy final, would also do. So using this principle or law, determine an expression for the spring constant in terms of quantities that can be obtained from measurements made with equipment usually found in a school physics laboratory. So starting from conservation of energy, initially there's only spring potential energy, which is 1/2 kx squared, and that's going to equal the kinetic energy, 1/2 mv squared. So cancel these two out, and you're left with kx squared equals mv squared, and then you get k equals mv squared over x squared. So this would be the experiment where you just launch it horizontally and you find the velocity. So if you decided to launch it like from a table, from a height, and find the displacement using kinematics, this would be your equation for K. Or if you launched it vertically and found the max height and made spring potential energy equal to the the gravitational potential energy, this would be your equation here. So you get 1 point for using conservation of energy. You get another point for simply using an equation that has K and the measured quantity. So something like this here. This would also get you another point. And then finally, if you correctly solved for K, that would also result in another point. Okay, so for part B, design an experimental procedure to test a hypothesis in which the student uses a launcher to launch the sphere. And okay, so I'm going to use the simplest one, which is going to be just launching it horizontally and finding the velocity. So first, we need to find the mass of the sphere. So, mass of sphere. And that's going to be m, and we're going to use a scale for that. And then second, we want to measure the displacement of the spring when, you put it in each pin position. So, displacement of spring, and that's going to be x, and we're going to measure that using a meter stick. Finally, we want to find the velocity after it's launched, so let's say final velocity, and that's going to be v of f, and we're going to use a photo gate. If you don't know what a photo gate is, here it is. Okay, so for part B, describe the overall procedure to be used to test the hypothesis, and include any steps to reduce experimental uncertainty. Okay, get another point for listing measurements that can be used to find K. So you get another point for using a plausible procedure, meaning it can be done in a physics classroom. So this can definitely be done in a physics classroom, so you get another point for that. And then you get another point for repeating the experiment with at least 2 different pin positions. So we said each pin position, which is A, B, and C, so that would be another point. And then repeat 3 times for each pin position, then that's another point. So in total, you get 5 points for part B. Okay, so for part C, describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis about the spring constant. So for part C, if your calculated K value for all 3 points are about the same, we can confirm the hypothesis. And if not, we will disconfirm. And so you'll get 1 point for mentioning the 3 different points, A, B, and C. And then you will get another point for addressing the experimental uncertainty. So if you said if your K value is the same or exactly the same, you will not get this point. Oops. So for D, a student uses a launcher to launch spheres that have the same diameter but different masses. So each sphere is launched from position A. So in order to figure out the graph, we want to find a function for the velocity, and we can do that by starting with conservation of energy again. So 1/2 kx squared equals 1/2 mv squared. But this time we solve for v, and that's going to be v squared over kx squared over m. So v equals the square root of kx squared over m. So from here we can see that velocity is proportional to 1 over the square root of m. And so this means that as m increases, velocity is going to decrease. And what I meant to say here was that since m is in the denominator, as m increases, velocity is going to approach 0. It's going to look something like this. Something like that. So you get 1 point for having a decreasing slope, I guess, or a decreasing graph. I'll give you 1 point. And then another one for having a concave up graph. That'll give you another point. And that is all for this FRQ.